Hi guys, welcome to another session of trigonometry and geometry, that is unit 3 of the IB diploma. In this session we will be introducing the unit circle. Okay, in introducing the unit circle we will define the unit circle and its 4 quadrants. We will use the unit circle to arrive at a more robust definition for trigonometric ratios, including sine, cosine, and tangent. And in doing so, we will say goodbye to the SOHCAHTOA method that we've been using from lower primary school, upper primary school to secondary schools. And we will use this new definition to find the trigonometric ratios for angles that are greater than angles that are all angles actually, including angles that lie that go beyond this range of 0 and 90 degrees. Okay. That means we can find the sine, cosine, and tangent of 120, 150, negative 200, any angle other than between 0 and 90, which this method of SOHCAHTOA usually helps us find. Okay, so and let's begin. So a unit circle is any circle of radius 1, that would be 1 millimeter, 1 meter, 1 centimeter, and so on. It doesn't really matter, just a unit of 1. Okay, and a unit circle would be centered at the origin of the xy plane. All right, so here is an example of a unit circle. The unit circle has got 4 quadrants, as you can see. In other words, it's divided into 4 parts. This is referred to as the first quadrant. That is the quadrant that lies between the positive and the negative positive x and y axis. All right. The second quadrant, so that's the first quadrant. The second quadrant lies between the negative x-axis and the positive y-axis. The third quadrant lies between the negative x and y-axis, and the fourth quadrant lies between the positive x-axis and the negative y-axis. Okay? Right, so what we see here is a unit circle. I've introduced a point P on the unit circle. The point P can move about the unit circle starting from point A there, the point where point A with coordinates 1, 0, like that. Point P, the line joining the origin to P, line OP, makes an angle theta with the positive x-axis, all right? And as point P moves around the unit circle, the angle theta increases. We will look at what happens to the height of point P and the distance of point P from the y-axis as point P moves around. In other words, as the angle theta increases, what is happening to the height? All right, let's stop there. So what is happening to the height of point P, the height, or if you like, the vertical distance of point P from the x-axis and its horizontal distance from the y-axis. Okay, and this is how we are going to define the unit circle. So first we will introduce a line, a vertical line from point P to cross the x-axis so that it crosses the x-axis at point C. Let that line be line S, and as you can see now, the length or the height of S is 0.719. As point P moves, of course, as point P moves towards the top there, the height of S is going to change. Let's also introduce another line that connects at point B, all right? And this line, we will refer to it as line C, but it is the same as OC there, so we don't need to include that there. Instead, we will put it down here because that distance there is the same as the distance BP. Okay, so that distance BP, let's call it C, and as you can see right now, the length of line C is 0.695, and it is positive because it's on the positive x-axis. Line S is positive 0.719 because it is on the positive x-axis. All right, I'm also going to introduce, as at this point here, this has to be 90 degrees so that we can think about triangle OPC. Okay, so that angle there is 90 degrees. So we can use our current knowledge of trigonometric ratios, sine, cosine, and tangent, to determine the sine of this angle, the cosine, and the tangent. Okay, the hypotenuse OP, taking this to be O, the hypotenuse OP is equal to 1 because this is a unit circle. Okay, so what we're going to do is now let point P move around again as it was doing, and let's see what happens to this distances S and the distance C. Okay, so you can see as point P moves up and down or moves around the circle, the length of S, or the height S, becomes bigger and then smaller to 0, and then now it is negative. Okay, so S indicates the magnitude of the line, but we know it is negative because we are on the negative y direction. Okay, similarly, if we look at C, it is increasing. When the angle is 0, C is 1, and as the angle becomes bigger towards 90, C becomes 0 at 90, and then becomes negative. This indicates the magnitude rather than the direction in which it is, so you don't see that negative there. However, we will see why it is negative. One other way of looking at point P is to think about the coordinates. So I'm just going to stop it for a moment when it gets to the first quadrant. Right? It is in the first quadrant. If I stop it there, let's stop it there. And what I'm going to do is to place the coordinates of this point. And so with the coordinates indicated as such, we can now see that we can see the x and the y coordinates of point P as P moves forward. So at that point, the x coordinate is 0.788, which indicates the value of C here. The y coordinate is 0.616, which indicates the height of point P. Now, as P moves around, we can see that at some times the y value and the x values are positive, and sometimes they are negative. So right now both are positive, looking at the coordinates of point P there. When we get into the second quadrant, the y coordinate, the x coordinate is negative, that the value of C is negative, the value of P is positive. When we get into the third quadrant, both x and y coordinates are negative. And when we get onto the fourth quadrant, only the y coordinate is negative, the x coordinate is positive, which makes sense when you look at the diagram. Okay, so this is the circle that we use to define trigonometric ratios, the sine, the cosine, and the tangent of an angle. All right, let's take this back to a point such as that, right? And we will use this position with our original definition of trigonometric ratios to find the length, to find the relationship between theta and the height, as well as the length C. So we will find the relationship between theta, S, and C here. Okay, so here is our point P, as we saw earlier on the GeoGebra simulation. The height of PC is represented by letter S. The horizontal distance there to point C, horizontal distance of point P from the y-axis is represented by C. So, looking at this, we can use our original definition for sine, cosine, and tan, basically SOHCAHTOA. So when we write SOHCAHTOA, this implies that the sine of an angle theta is the opposite of a hypotenuse. So this we know. this says that cosine of theta is adjacent over hypotenuse, and this says that tan of theta is opposite over adjacent. We will not spend too much time on this. We use it right now just to define that height and the horizontal distance, and then we will stop with this. So looking at these definitions with our right angle triangle there, we can see, remember this distance here is 1 because this is a unit circle, and therefore by this, sine of that angle theta, this angle here, is the opposite side to that angle divided by the hypotenuse. So it's basically s over 1, which is to say that this s is actually the sine of the angle. So by definition, the sine of angle theta is, on a unit circle, is the height or the vertical distance of point P from the x-axis. All right, so it doesn't matter whether it is on this side, on this, on the second quadrant, or the third quadrant, or the fourth quadrant. The distance of point P, vertical distance of point P from the x-axis, will be used to define the sine of the angle. So the sine of an angle is the vertical height of any point P on a unit circle, and that height is measured from the x-axis. Okay. Similarly, we can see that cosine of theta is adjacent over hypotenuse. So by the way, I've used this letter S intentionally to imply sine theta. So that height will always represent the sine of the angle. So instead of always thinking of SOHCAHTOA, go to the unit circle, and the height of point P on the unit circle will represent the sine of the angle theta. Similarly, cosine of theta is adjacent over hypotenuse, and the adjacent to the angle there is C, so we can say C over 1, okay, and therefore in the same way the cosine of the angle is the horizontal distance of point P from the y-axis. So but that is by definition. All right, and the tangent of an angle is the opposite over the adjacent, and because we have said this is the opposite, and it is sine of theta, and this is the adjacent, which is cosine of theta, we can easily write tangent of theta to be sine of theta over the cosine of theta, like that. And this is how we will now define trigonometric ratios for sine, cosine, and tangent. And what I want us to see now is that in the first quadrant, we have a positive x-axis, and we have a positive y-axis, and therefore both s, that means sine of the angle, and cosine of the angle are positive. Okay, so as long as the angle is lying between 0 and 90 degrees, both the sine and the cosine of that angle will be positive. And so going back to the GeoGebra simulation, we can see that while we are in the first quadrant here, both the height and the horizontal distance are positive, and so these values are both positive. This represents the cosine of the angle, and that represents the sine of the angle. So we can represent the coordinates of point P on the unit circle using the sine and the cosine. So this is the cosine and the sine of angle theta. So this is cosine of angle theta, and this is the sine of angle theta. So in the first quadrant, both the sine and the cosine are positive. So the cosine of this angle here is positive, and the sine of the angle is also positive. In fact, let me also introduce the angle directly now. We should be able to see. We can put the value for the angle. Okay, and we can see, let's start where we were. So we can see that as we start from 0, at that point the sine of the angle is 0, so that sine there is 0, the cosine is 1. So when the angle is 0, the cosine is 1. So cosine of 0, angle of 0 is 1. The sine of angle of 0 is 0. Now as I increase the angle, let's see, so I'm going to increase this to 30 degrees, for example. We can see that the sine of the angle is now 0.5, positive 0.5. The cosine is positive 0.866. This we will see is equivalent to the square root of 2 divided by 2. Okay? As we increase the angle, we can see the sine of the angle is increasing as the angle increases, but the cosine of the angle is decreasing. Okay? At 60 degrees, we have the sine of the angle is 0.866, which is root 3 over 2, and the cosine is now 0.5. And as we continue to increase the angle, now we are at 72, the sine of the angle is increasing, the cosine is decreasing. Okay, at 90 degrees, the cosine is 0, cosine of 90 is 0, but the sine of 90 is 1. And I continue to increase the angle. My angle is now 102. It should be evident that the value of the cosine is now negative because cosine refers to the horizontal distance from the y-axis, and now that horizontal distance is on the negative x-axis, and therefore this value is the magnitude, but it's actually negative 0.208. So as I continue to increase that angle, we can see now the sine is decreasing, so the sine is still positive, but the cosine is now negative, which makes sense because that distance is now on the negative side. The height is still on the positive y-axis, so this should make sense. So in the second quadrant, we can see the cosine is now negative. The sine is still positive, all right? So we can conclude that in this first quadrant, sine is positive, cosine is also positive, but as soon as we get here, sine is still positive and cosine is now negative. Right? We can move on. As I continue to increase the angle is now 139, and as I continue to increase that angle, I go to 180, for example. The cosine of the angle is negative 1. This shows here. The cosine of the angle is showing here. It's now negative 1. Well, not yet. Did it pass? Right, so now the cosine is negative 1, but the sine is 0. So cosine of 180 degrees is negative 1. The sine of 180 degrees is 0. Clearly, using the unit circle, we are now able to give cosine and sine angles for other angles other than between 0 and 90 degrees. We could give a cosine value to, let's say, 100 and 150, which should be popular or famous. We'll see the usefulness of this. So 150 as a cosine value of negative 0.866 and a sine value of positive 0.5. Now if you remember, we found sine of 30 was also 0.5. Therefore sine of an angle of 30 degrees is equal to the sine of an angle of 150 degrees. Okay? The key here is that using the definition of height of point P and horizontal distance from the y-axis, we can now determine sine and cosine of angles that are beyond 90 degrees or less than 0 degrees. Now let's move on. So beyond 180 degrees, we can still find the sine and the cosine of an angle. As you can see, both sine and cosine are now negative. So we can say that in this quadrant here, the sine of the angle is negative and the cosine is also negative. So the cosine is also negative. We move on. So sine of 214 degrees is negative 0.559. The cosine of 214 is negative 0.829. Let's increase the angle. 225 is a common angle that you will get to know. The sine and the cosine are the same, and they are both negative 0.707. That is the same as 1 over the square root of 2, or square root of 2 divided by 2. As we continue, 240 is another popular angle, or an angle you will get to know intimately. And when we are there, you can see that the sine of the angle is negative 0.866, or negative root 3 over 2, while the cosine of 240 is negative 0.5, or negative a half. All right, we can go on. At 270 degrees, we can see the cosine of the angle is 0, while the sine of the angle is negative 1. Remember, the sine refers to the height of P, or the distance, the vertical distance of P from the x-axis, while the cosine refers to the horizontal distance of P from the y-axis. So this makes sense, 0 and negative 1. As you continue, you can see now in the fourth quadrant, the cosine is positive, but the sine is negative. These are important pieces of information. So now we notice that the sine here is negative, but the cosine is positive, like that. All right, and so as we complete a full cycle with point P, we can make some useful conclusion, right? Let's talk about tangent. We agreed previously that the tangent of an angle, tan of theta, is sine of theta divided by cosine of theta. And that means we can use sine and cosine to determine where tangent is positive and where it is negative. So here, sine is positive and cosine is positive. So when you divide a positive number and a positive number, we get a positive number. So the tangent here is also positive. Okay, so in the first quadrant, all the trig ratios are positive. In the second quadrant, sine is positive, but cosine is negative. A positive number divided by a negative number is a negative number. So the tangent of any angle that is in the second quadrant, that means angles lying between 90 degrees and 180 degrees, their tan values are negative. Okay, in this case, both sine and cosine are negative. If you divide a negative number by another negative number, you get a positive value. And so from here, the tangent is going to be positive, right? In the fourth quadrant, so what we are saying here, that angles lying between 180 degrees and 270 degrees have tangent values that are positive. So tangent of 225, for example, would be positive 1, okay, and so on. In the fourth quadrant, sine is negative and cosine is positive. Again, a negative number divided by a positive number, according to this, will give us a negative number. So in the fourth quadrant, the tangent of the angle is going to be negative. So one of the conclusions we make is that in the first quadrant, all the trig ratios are going to be positive. Okay? In the second quadrant, only, I think I should use a different color. So in the first quadrant, we can say that all the trig ratios are positive. Sine, cosine, and tangent are positive. In the second quadrant here, we can see only the sine of the angle, any angle lying between 90 and 180, only the sine is going to be positive. So only sine is positive. Sine is positive. In the third quadrant, we can see only tangent is positive. So here we say tan. So tan of theta is positive. And in the fourth quadrant, as you can see, only cosine is positive. Cosine is positive. All right, we can draw a conclusion. There are different ways different students remember this. This is an important result that you need to remember. that when you're looking for the sine, the cosine, and the tangent of angles in a unit circle, all ratios are positive in the first quadrant, only sine is positive in the second quadrant, only tangent is positive in the third quadrant, and only cosine is positive in the fourth quadrant. This information helps us find angles, trigonometric ratios for certain special angles, as we will introduce, all right? We'll introduce later, all right? How do we remember this? I was taught by my teacher to remember this going in the anti-clockwise direction, that all science teachers cheat. So you can remember it in any manner that you like, that all in the first quadrant, sine, tangent, and cosine. All right. So you can remember this in any way that you like. I've seen different ways that students try to remember this, but choose your own way of remembering it. This is how my teacher taught me, and I've remembered it to this day. Okay, why is this useful? If somebody was to ask us to find the sine of 225 or 240, I will know immediately that the angle is 240, meaning it is in the third quadrant. The sine value has to be negative, okay? So sine of 240 would be the same as sine of 60, except it's going to be negative. Now, how do I determine that it is 60? We're going to see that very shortly.